Okay, can you hear now?
Yes.
And you can see now. Okay, I'm sorry. I mean, I was teaching with the iPad. I gave so many lectures, and this just threw me off completely. Okay, so Q for the talk will be acyclic, simply laced, finite type ADE. So it's a simple problem. N will be always the number of vertices. E will be Euler matrix for the quiver. And you can get from the quiver by just putting -1 when there's an arrow. There's an arrow -1, so that's the Euler matrix, or you can define in terms of Hom and X. I will use this pairing to be the Euler pairing, so for any V and W in Rn. So this symbol will be for Euler pairing, meaning product with Euler matrix. Phi plus will be positive roots as always, and rep Q will be finite dimensional representations over Q. And the point is that positive roots correspond to indecomposables, and I'm writing this here because I will be using this notation. So dimension of a module corresponds to dimension of the module indecomposable, and which will be positive root, or if I start with positive root, then M beta stands for the indecomposable module, which has the dimension vector, that positive root. So I will be using this notation, that's why I'm repeating it. And this is just the way it works on this simple case of A3. These are the representations, and these are the dimension vectors. Notice I'm using one to be the simple projective. So this is orientation. Some people use the other orientation, so I just want to point out that I'm using this orientation. Okay, now with that notation, we define d beta. So d beta is the set of all vectors V in Rn, such that their Euler product, Euler bilinear is 0, and Euler is less than or equal to 0 for all submodules of M beta. Okay, this is for beta positive. Oh, I didn't write here. So I will be, usually when I write beta, I will not use beta for anything else but positive root. Okay, so d beta defined this way is a hyperplane, or it is a part of hyperplane, right? So the first part, this part gives a hyperplane, and putting this condition also kind of indicates that we may be looking at part of a hyperplane. So here are the basic things that will be used. If N is indecomposable representation of Q, then dim N, so the dimension vector of N, will be on d beta as I defined above, if and only if Hom of N and M beta is 0, and X of N and M beta is 0, meaning that N is in the left perp of M beta, left perp, Hom, and X perp. So when I put here perp and put 0 and 1 means Hom and X perp. And that is if and only if M beta, this is beta here, oops. This is M beta, is on the right perp of N. Now, as I pointed out here, d beta is a hyperplane. So, or part of a hyperplane. Then we take all of these d betas, take union of all of those. So it will be hyperplanes, and so, and then we intersect with Sn in order for several reasons. One reason is because it's easier to draw things after that, and you can see it better. And we call it LQ, or we call it semi-invariant picture. I know that at this place, maybe mentioning word semi-invariant picture is not appropriate, but these are the domains of semi-invariance, and that's how we introduced this picture, and that's how we started to talk about that picture. So what it means is just that, right, I mean, you have a certain planes and then you intersect, and then you get these so you take hyperplanes, and then you intersect with this circle. Hyperplanes intersect with the sphere, and Sn-1, everything is in Rn. So I just want to mention some properties which will be used, because since I'm talking about homology of the picture group, I have to define picture group, and I have to define picture space, and so on. So here are some important things that I want to mention about this. So triangulation of Sn-1. So this, taking all of these and intersecting with Sn-1 gives us a triangulation of the sphere Sn-1. So that's one important thing that will be used. And the other is that we do get a normal orientation on each of the d betas. And the normal orientation is induced by the vector beta. So on whichever side is the beta, we consider positive, and the other side to be negative. So we do have, this is important part. We do get normal orientation on each of these d betas. Okay, now we take this picture. So this is what I said, and here is, we take a stereographic projection away from the vector -1, -1, -1. So all of this is on Sn-1, meaning S2 in here, because I'm talking about A3, N is 3. And this is a stereographic projection of all of these intersections. And I'm also using, so these intersections, we use hyperplane to be d beta, but I'm also using the same d to stand for the intersection with the Sn. So these are the d betas. Some of them, so when it is full circle, that means it corresponds to a full hyperplane, or some of them are partial circles, which will correspond to a partial part of the hyperplane. And now I want, oh yeah, important thing is that we will be also using is that the curvature. So we do this stereographic projection, and then we can see curvature on this picture, and curvature keeps information about orientation. So actually, whether it's curved this way, this will be positive side, this will be negative side. So the orientation, this normal orientation of the hyperplanes is preserved on this projection picture. Now, this picture I drew many times. It has interpretations in cluster algebras. It has interpretation in cluster categories. And today I actually want to concentrate more on this being a K picture in a formal way as a K picture. I want to define a group to this K picture, and then a picture space. Now, I gave talks about this group and so, but I actually never really described very much this picture space. So I think I want, in this talk, I would like to kind of give also a bit more information about the picture space. Now, as I said, it has interpretation in cluster algebras. And of course, in cluster, oh, I already mentioned this. In cluster algebras, let me just do it this way. Okay, I'm not going to repeat. This was my general public talk about about cluster algebra. So I'm not going to repeat that. You know, it was Fomin and Zelevinsky who introduced them. We have initial cluster, we have so initial cluster, we have mutations, and we have clusters. We have C vectors, and the C vectors have sign coherence. But I want to talk about the picture. Notice it is the same picture as my semi-invariant picture that I just had previously, but now I'm labeling. So each of the vertices is labeled by a cluster variable. So these are these monomial, the rational functions, which are cluster variables. I have initial cluster x1, x2, and x3. Each of the triangles corresponds to a cluster. Going from one triangle to another triangle corresponds to mutating cluster variable from this cluster to cluster variable now in this cluster. So this is just a cluster algebra terminology. The lines, which are the domains of semi-invariants, which I denoted with D something, these are the C vectors. So each triangle is a cluster, and the lines are corresponding C vectors, and the green sign stands for the positive C vector, and the red sign stands for the negative C vector. So on this picture, I have labeled everything cluster variables, clusters, mutations, C vectors as being positive and C vectors as being negative. So that was all that I wanted to repeat, that the same picture has that information. And then I said, we have cluster categories. And then again, I'm not going to talk, I mean, in this audience, I did not want to talk much about cluster algebras and cluster categories because people know. But again, cluster category, we have the object, we have representations, we have the derived category, we have the orbit category, and this is the fundamental domain. And I want to point out on the same picture, so exactly the places, and this is what will be used because I'll be talking about picture groups. So I really need this formal way. So the vertices which corresponded to cluster variables now correspond to the indecomposable objects in the cluster category. Initial cluster in the cluster algebra corresponds now to the shifted projectives. So initial cluster corresponds to the shifted projectives, and all the other clusters correspond to the indecomposable modules. So this is just, again, the same picture, but in terms of cluster algebras and in terms of cluster categories. Okay. And then again, clusters correspond, cluster tilting objects. Oh yeah, I will be using that. So cluster tilting objects correspond to triangles. Rigid objects correspond to parts of the triangles. This is like rigid object. And mutations correspond to crossing the lines, which is crossing C vectors from positive side to negative side of C vectors. So everything, all of the cluster terminology has interpretation on this picture. Okay, so this is what I wrote here. And now I want to talk really formally about K pictures. Okay, so a K picture, a definition of a K picture, L, is K minus one dimensional subcomplex of a triangulation of a sphere SK. So it has to be subcomplex of a triangulation, which in this case we actually have triangulation, but we often need to take just the subcomplexes instead of the entire. Then we need normal orientation on K minus one simplices. And we need normal orientation on K minus two simplices. Okay. And the proposition which is being used is that if we start with Q, quiver of type ADE, N is the number of vertices, then the semi-invariant picture LQ, which I defined above, is an N minus one picture in this formal way of being a picture. And the reason, well, first of all, LQ is actually many people like to view this as a simplicial complex, with simplices being given by rigid objects in the cluster category. So that's what I kind of pointed out on the picture when I was talking about cluster category. Now, D beta are unions of N minus two simplices. So notice I have A3, so I'm on S2, and then my lines are one simplices, right? So D beta is union of N minus two simplices, And we have normal orientation on d beta, as I pointed out, and that induces normal orientation on these n-2 simplices. So let me just go back to the picture here. So this is ds2, and it consists of, this is one simplex, this is another one simplex, one simplex, one simplex, and one simplex. So d beta consists of these one simplices, and d beta has orientation, which induces orientation on each of these one simplices, and that will be used throughout the part. Now, the other part is I also need normal orientation on k-2 simplices. So on this picture, this is k-2 simplex, okay? So orientation will be choosing orientation like that or orientation the other way. But the formal way, I just want to point out what is the formal way. Yeah, n-3 simplex. The vertex is 0 simplex, so it is n-3 simplex. So the formal way, and I'll just kind of quickly point out. So n-3 simplex row on Sn-1 is given by a rigid object with n-2 summands. So if you take the right perp, so here's this rigid object, which I call U. If you take right Hom X perp, it's an abelian subcategory of rank 2. If it's a abelian subcategory of rank 2, it has simple objects. So we take m beta 1 and m beta 2 to be simple objects in this right perp category. Now, these beta 1 and beta 2 determine hyperplanes. And then we take note, notice there will be hyperplanes. So then we look at the R2 plane, which is normal to the span of this n-2 t's. And it is also normal to these hyperplanes d beta 1 and d beta 2. Okay, so starting, okay, n-3 simplex corresponds to n-2 summands, which are rigid. That gives us 2 Hom orthogonal modules, and they correspond, this is rho. So beta 1 will give us one domain of 1d beta, beta 2 will give us another one. And at that point, because this is two-dimensional space, it will be like that, and it might have another line here, okay? So each of these, so this part, this n-3 simplex corresponds to a point like that, and each part will look either like that or like that. That is for simply laced. I'm emphasizing that's for simply laced. It's not true. If when we look at the modulated, then you may have more than this. For simply laced or finite type, okay? And this is what gives us, so once we have that, then we decide, do we want beta 1 first and then beta 2 second, which gives orientation this way, or we decide this way. So a choice, so rotational orientation is decided or determined by the choice of ordering of beta 1 and beta 2, which are simple objects in the right perpendicular category to our rigid object. Okay, so this now says that the semi-invariant picture is a n-1 picture in the formal way as being n-1 picture. Okay. Now with the picture, we define a picture group. So now I'm going to define a picture group. So again, my Q, I'm just repeating that Q is ADE. LQ is the semi-invariant picture that I defined previously. And now picture group will be given by generators and relations. We take X to be all X betas for beta. So we just define X to be set of all X betas for beta in a positive root. And then we label, okay, so this is the part, we label all n-2 simplices which are on the same d beta by x beta, okay? So let me just do it here and I'll come back. So here I have ds2. This is one of my d's. Now I label every single one simplex on that d beta with xs2, so every one of them. This is ds1, so every simplex is labeled by xs1. This, and this. Of course, this part here is dp3. So there'll be these two simplices which will be labeled with xp3. So now let me just go back to, okay, so I'm defining picture group as group generators and relations. Generators are all x betas for beta in being a positive root. I label everything on the same d beta with the same x beta. And now I need to define what are y's. So y's, so now I look at each row, which is n-3 simplex. So which in A3 is just a vertex. And I define y row in the following way. Y row is a product of x sigmas, which were these x sigmas, are raised to epsilon. Here's epsilon sigma, which is plus or minus, and it will depend on the orientation of d beta. And I do product over all sigmas which contain rho. So sigma will be now n-2 simplex. Rho is n-3 simplex. These are all sigmas which contain rho. And I take product of all of these x sigmas, and it is with plus or minus. So it will be, I just wrote here, product follows orientation of rho, which means we'll be going around. And maybe I'll just do it here again. So if this is rho, then the product will go around that rho, and orientation of rho, that means I decide either I'm going this way or I'm going this way. And then the sign on each of the sigmas will be plus if I'm coming from this direction, or minus if I'm going from this direction. So let me just illustrate this on the example that we have. Okay, and I actually wrote all the relations. So first of all, generators correspond to every positive root, which is to every indecomposable module. So the generators correspond to all d betas, and d betas correspond also to positive roots, which are positive c vectors. So I want to kind of emphasize that this is actually here correspond to the c vectors at various places. And then y, let me just do this one, oops, here, oops, okay. So this y here, which correspond to this row, so I chose orientation, and then it goes xs1, then xs2. Now I'm going in the opposite orientation on ds1, so it goes xs1 inverse. This is xp2, so xp2 inverse and 2 inverse, and that is this. And if we look at P2, in P2 we'll have only S1, S3, S3 inverse, S1 inverse, S3 inverse, and I just wrote all of them. Notice that ones around shifted projectives and ones around projectives are either the same or of the inverse to each other, and that is how the group G is defined. And this is just a remark. Multiplication, that is, okay, so here, this I'm talking about this part here. So multiplication is crossing walls which are labeled by C vectors. So the multiplication is really crossing walls and keeping track of the orientation of both n-3 and n-2 orientations. And relations are given by sequences of crossing walls with appropriate signs, as I pointed out, around a fixed n-2 piece of cluster or n-2 rigid object in the cluster category. So the relations are always going around n-2 rigid objects. I mean, rigid objects which have n-2 summands. And this is the group. Okay. So remark, here's just my quick remark. There are other nice presentations for the same group. Oh, this is what we call picture group. But this is a good one for the homology and also for good, I want to discuss a little bit relation with the unipotent group, which I will define now since last time I didn't define. Okay, so some general properties. Greg, can you tell me time because I started, I don't know when I'm.
No problem. You have about 4 minutes or so.
4 minutes, okay. Okay, so some general properties. Okay, so relations are given
5 minutes or so. Yeah.
5 minutes, okay. Relations are given like that for Hom X orthogonal or are given like that. So this is what people ask me about the relations. Okay, so they're either given of this form or of this form for simply laced. The other comment is that this group is torsion-free group. The other comment is, okay, so here I put this sign that there's epimorphism, and I just want to kind of discuss, mention this a little bit. Well, it's not question mark, it's actually exclamation, okay. If it is straight orientation, then there is a homomorphism. And we were just computing last night, okay, so if there is homomorphism, then the massive product is supposed to be 0. And if there is no homomorphism, which means it's not straight orientation, then a massive product should be non-zero. And that's what we are discussing. This is part of, so this part is kind of in progress, sort of in progress, okay? Oh yeah, and unipotent, last time Misha asked me, okay, so unipotent are just n+1 by n+1 matrices, ones here and z here. Homology of these groups here is given homology. And if you look at, so for A2, A3, and so on, AN, and so on. And people recognize these dimensions as being given by Belloc numbers. And notice there is no Poincaré duality here. And to compute homology, we use picture space. And let me just do quickly picture space. So picture space, we start with the quiver. We have our semi-invariant picture. We construct the dual cells. So I color them here in different ways with dual cells, okay? And then here's just a quick summary of how you create the picture space, okay? So you start with a cluster category, then you have semi-invariant picture, Then you create these dual cells, which are boundary, which give boundary of Sn minus 1, and then you identify things here. And if you start with cluster tilting object, which is n minus 1 simplex on Sn minus 1, then the dual cell will be 0 cell, which will be just 1 point. And then in the picture space, we send all of these points to one single point. Now, if we have almost complete cluster tilting object, it will be between two triangles. So it will be between two tilting objects. It will give one cell, and in the picture space, it will give one cell like that. Now, this is the important part. If we have two almost complete cluster tilting objects, which have the same Hom right perpendicular category, then they're on the same d beta, and we identify those two. So in short, for each beta, each one cell which crosses beta will be identified. So we'll have only one cell for E beta. And just on this picture, this is one cell, this is one cell, this is one cell, this is one cell, this is one cell. They all cross my DS2. So all of these one cells will be identified and give just one cell in the picture space. And then we attach this two cells. So here's my two cell, which we attach going around boundaries. So this is S1, so I go around S1 and then E2 and then S2 and then S3, the inverse. So I follow boundary here, and that is how we attach this two cell. So this is kind of bubbly, so it's a two cell, and that is how you get the picture space. And just a quick remark, why picture space? Picture space is K pi 1, which means for the picture group, which means that it just has pi 1 and no higher pi's. But the main point is that the homology of the picture space is the same as the homology of the picture group, and the homology of the picture space is easier to compute. So that's kind of idea of picture space. And these are the picture groups depend on orientation. Homology does not depend on orientation. This is all for AN. I forgot to write for AN. So homology does not depend on orientation. Cohomology does not depend on orientation. But if we look at the massive products on the cohomology, it depends. And this is the part that okay, I'll stop at this point. I think this is, thank you.
Thank you very much, Gordana, for a beautiful talk. Are there questions in the room?
There seem to be no questions in the room at the moment. Greg, can you hear me?
And yes,
Okay,
sorry.
good.
Any questions? I was just giving people a second. Are there any questions in the Zoom audience? I wanted to ask about the numerology. Do you know anything about what happens with the homology in the type D case?
No, we didn't do that. I don't know. Oh yeah, I didn't mention these numbers, right? These are ballot numbers. I guess for people in combinatorics, these are interesting numbers. Okay.
Any other questions? In that case, I want to thank Gordana again. And let's have a round of applause for all the speakers of today. And I also wanted to thank all the speakers for the week, and as well as the organizers and the staff of Isaac Newton Institute.
Ja.